Thank you everyone for staying up to the last talk. So I'm going to talk about the most recent or latest work on from Professor Arakawa. So I'm going to talk about the unified parameterization. And after a few years, we finished the paper on the unified parameterization. Professor Arakawa asked me, and he said, why doesn't anyone use this parameterization in a model? And then I look around and I said, I found that all the model developers want to use their own parameterization, so they don't use my parameterization, our parameterization. So I come up with the discussion with the Weather Bureau in Taiwan and ask them if that allow me or let me to try to implement the unified parameterization. So my student Jun Yan, he did a lot of work in this, so he sort of implemented the idea of unified parameterization in the Central Weather Bureau model. So I'm going to walk through these ideas and show some results of his unified parameterization. Okay, so I started with the slides from Professor Arakawa in 2010, and I know that everyone brought up pictures from Professor Arakawa, but to me that this is sort of the picture of Professor Arakawa. He sort of do this nice, elegant slides. So if you sit with him and see him walk through these slides, you will tweak every detail on this slide. And he has a specific selection of colors. It's hard to find from the PowerPoint. So this is a carbon copy of his slide. Okay, so the goal is to have a unification from the general circulation model to the global cloud resolving model. There are two routes, and the unified parameterization is one of the routes. So he sort of think of this convective parameterization has to have a horizontal area large enough for ensemble cloud, but small enough cover only a fraction of the large-scale disturbances. But as Dave told yesterday, we're always in the gray zone, so we always have to deal with this cannot cut it clear problem. So the unified parameterization is trying to sort of unify through the changing this assumption called a convective object fraction. So most parameterization assume that the convective object fraction is small. So the parameterization is actually formulated for the environment, as we show in the left figure. But if you think of the increase of the horizontal resolution, so at some point, the convection will occupy a whole grid point. So there's no room for the environment. So at this point, the assumptions sort of break up. So a key to open the route is to eliminate the assumption of sigma much less than 1. This is idea for the unified parameterization. So by doing so, we sort of retain the sigma in the mass flux parameterization. This is some kind of go through for the traditional parameterization is to make the assumption of sigma smaller, much less than 1. So we can formulate our eddy flux, the 5 bar, as this mass flux formulation. But for unified parameterization, we have to retain the sigma so that the eddy flux will be something like that in the formulation. And then we have to determine what sigma looks like and then close this formulation. So before that, we did analysis from the cloud resolving model, as Steve showed in the previous talk. We found that many people think of this unified parameterization as a sort of a scale-aware parameterization, meaning that changing resolution and it changes the parameterization. But for us, it actually has more delicate properties because if you look at the eddy flux divided by this total flux, this is calculated from the cloud resolving model results. So the x-axis is the resolution, y is the sigma. And you see, take the 16 kilometer, for example, you see that as the cloud fraction is small, the eddy flux sort of covers all the transport. But when you have larger sigma, it decreases to almost 0 in that sense. So all the flux is actually carried by the grid scale. You don't need the subgrid to do anything. So you can see that as the resolution go higher, you actually get larger variabilities of sigma starting as around 16 kilometer. So that's the resolution we are trying to use to implement this unified parameterization in the Weather Bureau model. Okay, so the concept of unified parameterization is actually very easy. So it's a closure to determine the eddy flux that's applied feedback to the grid scale through the formulation of sigma. So you can think of the W prime, eta prime, phi prime E is the cumulative parameterization produced eddy flux. And the W prime phi prime bar is actually what's a feedback to the larger scale. So it's sort of scaled by the 1 minus sigma square here. And this sort of, you can think of this idea as a relaxed adjustment, meaning that if you have large sigma, meaning the convection actually occupy a lot of area. So you don't have to use the subgrid parameterization to do the adjustment. You leave the room for the grid scale to develop. So I would think of this unified parameterization is to sort of set up a partition between the grid scale and subgrid scale processes. So that's sort of the main idea of the unified parameterization in this implementation. So, but we have to decide sigma, and we can use this some formulation, algebra change, to use the lambda as an expression for sigma. So when you have larger sigma, it means that you have strong destabilization, something like the convection core in the system or Dyno cycle over land. If you have a small sigma, it means that there's a small difference in the cloud environment properties, something like this stratiform precipitation. Okay, so here's how I implement in the model, and that the parameterization I choose is the relaxed Arakawa Symposium scheme. It's from the Morrison Suarez 1992. So it's, again, another relaxed adjustment scheme. So it's a sort of relaxed twice. So the relaxed Arakawa Symposium sort of adjust the total quasi equilibrium in time by doing this adjustment sort of partially in each time step. So we have a lot of equation here. On the left side is the framework of unified parameterization. So we have to determine each part of these parameters individually. The first one is the equilibrium adjustment of the found cumulus parameterization. That's sort of the mass flux parameterization in the RAS. The second one is the this cloud environment difference of this vertical velocity. Sorry, it's a cloud grid scale difference of the vertical velocity. So we have to decide it through this vertical kinetic energy equation. And then we have this property we can calculate lambda, and through solving this sigma equation, we can calculate the W prime phi prime bar, the eddy flux, through this determine the sigma from the URAS. So that's sort of the simplification for the formulation. There are a lot of detail in the RAS, because in the operational model, there are a lot of setup or parameters I don't really know, so I sort of have turned it off and to see if the model still works. But in the end, it actually worked pretty well as an original form of the RAS with the unified parameterization. It looks pretty okay. So the model is run at 15 kilometers, so that has the chance to have a large variability of this sigma. Okay, so there are some results here I show. So I do some high-case simulations and the statistics is calculated over the maritime continent. So on the left-hand side is the precipitation spectrum. You can see that the URAS sort of have a stronger precipitation spectrum compared to the original RAS. And we think that this is because the URAS can actually capture the convective system in respect to its precipitation. So on the right-hand side, you see the size of the convective system, and the y-axis is the precipitation. So in the observation, as the, sorry, this should be, black line should be the observation. The increase of the convective system size, the precipitation actually increased substantially. And sort of the URAS can follow this kind of development, while the RAS sort of only have the weak precipitation no matter the cloud size, convective object size. So if you look detail into the convective system, here's an example of the simulated convective system of the ocean. And so the left column is the RAS and right column is the URAS. So it's easy to see that you've got larger variability of the moisture inside the URAS, the convective system, and hence the higher precipitation rate there. And then you can see that the omega in the convective system in URAS is pretty significant in that in the system. So the vertical structure, so I cut through this system and see that the vertical structure. You can see that if you use the traditional RAS, you get no grid scale processes going on. But if you have this unified parameterization implemented, you see that the convection can actually build up with this mesoscale system and a strong vertical velocity there. One thing that's sort of interesting is to look into details of this sigma distribution and consider how this the closure influences this evolution of this convective system. But it turns out to be like a pretty messy map. But you can still see that within the black line is within the convective system, there are larger sigma, meaning that maybe this convective instability is strong, so the unified parameterization try to suppress it for the grid scale to develop in that sense. Okay, and so some overall statistics of the moisture space, and you can see that because of this, in the URAS, the moisture can sort of hold up longer or accumulate stronger. So the axis between the URAS and RAS is actually not the same. The URAS can have higher moisture and leading to higher precipitation in this calm water vapor precipitation spectrum. But the RAS sort of dry out pretty fast, so the precipitation pickup doesn't actually continue to the more moist environment. And if we look into the diurnal cycle of a land area, you actually see that the model with URAS actually perform quite well compared to the RAS. This is sort of referred to the diurnal cycle problem just in previous talk. So the traditional parameterization tend to follow the development of the diurnal cycle of the solar radiation, so it have to peak around noon or late early afternoon. But over mainland continent, the peak time is actually in the midnight. So this is sort of during the daytime, the convective instability sort of increase the sigma, so that in the early afternoon, the subgrid parameterization doesn't actually kick in and stabilize the environment, so that the instability can continue build up to later in the afternoon, and to the midnight, the grid scale convection can take care. Okay, so the diurnal peak time, you can see the some very nice improvement with the URAS. So in the RAS, as I just mentioned, it sort of peak, the diurnal peak is always around in the afternoon. But in observation, over mainland continent, the convection sort of peak in the afternoons at the coastline, but move toward midnight to the center of the island. So the URAS sort of behaves similarly to the observation in that sense. Okay, so this is last slide. So the development won't stop here. We want to have some stochastic process implemented here. So we want to go back to the root of this CloudWork function references to implement this this variability from the environment to introduce the stochastic effect for the URAS. And we think that the environment can be separated into at least land, ocean, or coastal region for 3 parts. And for the weather prediction, we were thinking a machine learning approach to model the discrepancy for the forecast system. Okay, thank you.
Okay, thank you very much. I think they had a question.
I missed, were these tests pure simulations or experimental forecasts?
It's hindcast.
Okay, but starting from observed initial.
Yeah.
Okay.
Real simulation.
So how does the skill score change?
I didn't calculate the skill score. So we just have something like this to demonstrate that.
Looks promising.
Yeah.
The skill score will be important.
Yeah. Yes.
So is there any chance that this would be adopted operationally?
Hopefully, yeah.